So before we can understand how to add together two rational expressions, let's go back to a simpler time, back in Module 1, and compare the problem that you have to work on here with the problem of adding together two fractions. Say the fractions are 7/3 plus 8/5. So I just sort of hid that y for the moment. Because the process should be exactly the same. Let's do it in the familiar case first, to remind ourselves of how it works in a more complicated case. So if I want to add these two fractions together, what should be the first thing for me to think about? Before I can add two fractions, I need them to have common denominators. And so between the two denominators, 3 and 5, I need to find a multiple, ideally the smallest common multiple, but really any common multiple will do, of 3 and 5, in order to rewrite each of these fractions to have a common denominator. So what denominator can I use to add thirds together with fifths? Yeah. And 15 you got by multiplying 3 and 5. Remember, that's a trick that always works. We don't always have to choose the lowest common multiple. We can just choose any common multiple for the process of adding together two fractions. So that tends to be the way I like to do it. Just multiply the two denominators together. In this case, that gives us 15s. And now that each of those are on denominators of 15, how do I change the numerators? So my old numerator here was 7. How do I figure out what new numerator belongs in the 7's place? Multiply by 5. So that's sometimes called taking the cross products. The 7 from the first fraction times the 5 from the second fraction gives me the numerator, 35, for the first fraction once we have the denominator of 15 down there. So here, 35 is the numerator of this one. How about for the second fraction? What replaces 8? All right, 8 multiplied by 3 gives me the second fraction. 8 times 3, 24. So, second fraction turns into 24 over 15. And now both of my fractions have common denominators. And now that they have common denominators, how do we add them together? What do I actually end up adding? Yeah, I add together the two numerators, 35 and 24. It gives me 59. And my denominator remains the same. So add numerators, keep denominators, 59 over 15. And then, can we simplify 59 over 15, or is it in its lowest terms? 59 over 15 is in its lowest terms because the only factors, the only prime factors of 15 are 3 and 5. And the only prime factors of 59 are, well, actually 59 is prime. So there are no factors in common to the numerator and denominator. So I can't simplify this fraction any further than it already is. And so our answer is 59 over 15. So that same process of adding together two numerical fractions, we can export that process into adding together two fractions that might have variables in portions of them, either the numerator or denominator. So if I do that, then to add together these two fractions, 7 over 3y plus 8 over 5, what can I use as a common denominator? Or what did you use as a common denominator when you did this problem? Same story as we did above, right? If I want a common denominator for my two fractions, I can just multiply together the denominators of my originals. 3y times 5 gives me 15y. And that will work as a common denominator for my two fractions. So we don't have to sweat finding the least common multiple to serve as our denominator. We can just take the multiple, just multiply both of them together. And if I multiply both denominators together, again, anytime you're adding fractions or subtracting fractions, we need that common denominator before we do anything else. And then once we have it, how do we find the numerators? What do we do in the example at the top of the board? Yeah, we're again going to multiply, take the cross products. So the first of my fractions, 7 over 3y, to find its new denominator, I'll multiply the 7 from the first fraction by the 5 from the second fraction. That's going to give me a new numerator here of 35. And for the second fraction, I'll do the opposite cross product. The 8 from the second and the 3y from the first. What's 8 times 3y? 24y. And now, both of my fractions are still equivalent to what they originally were, but now they're written with a common denominator. So after we found the common denominators by multiplying, our second step was to use the cross products to adjust the numerators. And now that we've used the cross product to adjust the numerators, how do we actually add these two fractions together? What do I actually end up adding? In our example at the top of the screen, we just added the 35 and the 24 and got 59. Same story here. We're going to add the 35 and the 24y. And when I add together 35 plus 24y, what do I get? Well, except that I don't. Because 35 and 25y are not like terms. When I add them together, we can't make it any simpler than 35 plus 24y. So it's not the same as 59y. It's not the same as 59. It's just 35 plus 24y. Because they're unlike terms, we couldn't combine them together. And so at that point, it kind of is what it is. Unlike terms. And now the only question that remains is there a way for us to simplify this fraction in order to reduce it into lower terms? And the only way to know, so now that we've done the add numerators process, the only way to know is to, and then this is important theme for today. Before we know whether we can simplify a rational expression, so it's got a polynomial upstairs and a polynomial downstairs, the only way to know is to factor everything in sight. In this example, factoring everything in sight was the last thing that we did. But the important thing about factoring is that we have to do it before we simplify. Because simplifying a rational expression takes the form of canceling, of taking any common factors to the numerator and denominator and crossing them out. In other words, dividing numerator and denominator by their common factors to get it into lower terms. We can't do that until we know what the factors are in the numerator and denominator. And we can't know what the factors are until we factor. So, because sometimes this is what I'll see. Sometimes I'll see people, and you might have done this on one of these kinds of questions in the past, because we hadn't had this conversation yet. But sometimes I'll see people take this fraction, 35 plus 24y over 15y, and say, oh, well, 15 and 35 share a factor in common. Right? What factor do these both have in common? (35 and 15? They both have a 5 in common. So why can't I just reduce this by dividing the 35 by 5 and dividing the 15 by 5 and get 7 and 3 and then have plus 24y here still? What's wrong with that picture? Why can't I do that? Because this is the kind of thing I see a lot of people doing on these kinds of questions because we haven't had this conversation yet. So what's wrong with just canceling a 5 out of those two pieces? Say again? Okay, well, they're not like terms, that's true, but that's not the reason that canceling a 5 out of them is inappropriate. Compare it to this. If I change the problem a little bit so that my answer was 35 plus 25y, so I'm going to replace the 24 there with a 25. So for comparison, I'm going to backtrack here and say that this simplification is not true, just for when you look back at this later. But if I had 35 plus 25y instead, over 15y, then what we would want to do is factor everything. Because now I can say that that 5 that we saw that was a factor in 15y, if I bring out a 5 from 15y, and if I bring out a 5 from my numerator, then I'll be able to see that 5 is in fact a factor of the numerator and denominator simultaneously, because in the bottom, 15y is equal to 5 times 3y. And in the numerator, 35 plus 25y is equal to 5 times 7 plus 5y. And in that case, because my 5 is common to the entire numerator and the entire denominator, I can undo the multiplication of fractions to split out that 5 over 5 by itself, and the rest of it, 7 plus 5y over 3y, by itself. But what is 5 over 5 otherwise known as? It's 1. And so since 5 over 5 is equal to 1, multiplying by it is the same as not multiplying by it, which is the same as not multiplying by anything at all, and so we've canceled it. Right? And so my point here, and this is the point that I don't want to get lost in the shuffle of everything today, is that there is no canceling until after factoring. Because the cancellation that we did in the bottom here, in this example, is legit canceling. This works because the 5 is a factor of the denominator, and it's also a factor of the whole numerator. The problem with our first stab over here is that, yes, 5 was a factor in our 35, but 5 wasn't a factor in 24y. And in order to be eligible to be canceled, it has to be a factor of the entire numerator and not just of one term in the numerator. So the way to avoid making that error is resist the temptation to cancel until after everything in sight has been factored first. If it can't be factored, then you can't cancel anything. Right? So after you've factored everything, then you can cancel those factors that are common. And if you do that enough, then you'll get to the lowest terms. And it's a little harder to do when things are polynomial expressions compared to when they were numbers. But from Modules 7 and 8, we now have a whole arsenal of factoring techniques at our disposal to help us do it, which begins with finding the greatest common factor of the terms, and then looking for the sum and the product game, using the AC method, looking at a difference of squares. All that stuff that we spent our time on in Modules 7 and 8 comes in handy when we're doing this, because it's the only way we know of to reduce a rational expression into its lowest terms. Therefore, the lowest terms for our final answer are the way we had them, 35 plus 24y over 15y. Because, in fact, I cannot factor the numerator, 35 plus 24y, in any meaningful way. Because 35 and 24 have nothing in common, nothing useful in common. 35 is a 5 and a 7. 24 is a 3 and a bunch of 2's. And so 35 and 24 have no common factors for me to bring out of 35 plus 24y. So since I can't factor it, I can't cancel anything. Can't factor, so can't cancel, which means that we must be in lowest terms, making this our final answer.